All right, new section, 3.6. In 3.6, we're talking about the chain rule. The chain rule is it's a fairly challenging topic, but it's super important. So I want to make sure that I really hit this hard. I have lots of different examples that I want to show you in these videos. I want to make sure this is really clear because this ends up being one of the more important, but also one of the more often misunderstood rules of a calculus class. I think the reason the chain rule is so challenging for students is because it's based on function composition. And function composition itself is kind of a complicated way to put together functions. So if students are kind of lacking that foundational knowledge, of course you're going to find things built upon it really difficult. So what I want to do first is kind of review some ideas with function composition. So the idea with function composition is you have to be given two different functions. In this case, f of x equals x cubed and g of x equals sine of x. And we want to put them together by composing them. And the way you write that is either like this or like this. The way we say what is written on the left here is f of g of x. And similarly, what's written on the right is g of f of x. This does not mean f times g, although a lot of people misinterpret it that way. When I'm teaching function composition in a pre-calculus class, what I encourage students to do is anytime you see this notation for function composition, rewrite it in an alternative notation. Equivalent to what we have here is this nested notation where we write the letters in the exact same order they appear here, but you don't write this composition sign, you instead just use another set of parentheses. So the way it would look would be f of g of x. What's written down here and what's written up here are equivalent, and in fact the way you say them are the exact same. In either case it's f of g of x. But writing it this way makes it easier to come up with an expression that represents this composite function. The way you do things is you just work from the inside out. What do I mean by that? The inner layer here is the function g of x. F of x is the outer layer. So I'm going to leave the outer layer completely alone. All I'm going to do is replace the inner layer, g of x, with what g of x is defined to be equal to, sine of x in this case. F of g of x is the same as f of sine of x, but the advantage to f of sine of x is it's something we can evaluate. The reason why is we have this blueprint for the function f of x right here, which tells us the output, x cubed, for any input x. So what we're being asked here is what would be the output of this machine if our input, instead of being the letter x, were the expression sine of x. So all we have to do is copy exactly what we see on this line, except change all the x's into sine of x's. And if you did that, what you'd end up with is the sine of x cubed. If f of x is x cubed and g of x is sine of x, f of g of x is sine of x cubed. Contrast that with what you'd get if you compose the functions together in this order, g of f of x. In that case, g is the outer function and f is the inner function. So if I were trying to evaluate this thing, I would start with the f of x, the inner function. You always work from the inside out. F of x is defined to be equal to x cubed, so I replace this f of x here with an x cubed. All that's left to do is evaluate g of x cubed. G of x is given up here, so all I gotta do is copy exactly what I see right here, changing all of the x's into x cubes. That leaves me with the sine of x cubed. These two things look really similar, but they're not the same at all. In this case, it's what comes out of the sine machine that gets cubed, whereas in this case, it's what goes into the sine machine, the x, that's getting cubed. Very different expressions. Function composition is not commutative. The order that you compose is really important. And maybe you're like, I thought this was a calculus class. I learned all of this a couple of terms ago when I took a pre-calculus class. Yeah, that's great. I just want to review this because what we'll see is taking the derivatives of these things are pretty challenging. And in order to take those derivatives, we have to be really comfortable with function composition, hence the review. But without further ado, let's talk about the derivatives of these guys. The question asks, could we take the derivatives, I guess, presumably with our current knowledge? And that answer is, well, kind of. Yes and no. It'll turn out that this expression over here is beyond our ability to take the derivative of, but this one over here is something that we can handle. Couple comments on this one over here. First of all, nobody writes it this way. When you have sine of x cubed, the standard is to write this as sine cubed x. This means the exact same thing as this. We put the exponent on the sine part so that the reader doesn't think it's the x that's getting cubed if we don't have any parentheses in there. It's not great notation. It tends to confuse students. Students think that the sine somehow is being cubed and then multiplied by x, which is not at all the case. What you need to know is when you see something written like this, it means sine of x cubed. That's my first comment. My second comment is, even without any knowledge of the chain rule, we can take the derivative of this thing. Because when you're cubing something, you're just multiplying it by itself 3 times. So if somebody asked you for the derivative of sine cubed x, really what they're asking you for is the derivative of sine of x times sine of x times sine of x. And when you view things in this form instead of this form, we have all the machinery necessary to take the derivative. This would be an instance of our super product rule, where we're multiplying together three things. What we learned in the previous section is you take the derivative of the first thing, so the derivative of this sine of x, which is cosine of x, and then you leave the other two things alone. So we got a sine of x and another sine of x. And then to that we need to add what we'd get when we took the derivative of the second thing, so this sine of x, which is also equal to cosine of x, times the other two things left completely alone. So another sine of x times sine of x. And then finally, we need to add to that what we'd get when we took the derivative of this last sine of x, again equal to cosine of x, leaving the first and the second sine of x completely alone. The derivative of sine cubed x is what we see written right here. However, there's no reason you have to leave things as they're written right here. If you're kind of clever, you might notice that what you have in the first term is identical to what you have in the second term, which is identical to what you have in the third term. So really, we have three of these cosine x, sine squared x things. The derivative of sine cubed x is 3 times the cosine of x times the sine of x squared. Cool, so that's the chain rule? No, not at all. We didn't use the chain rule at all to figure out this answer. Although we could have come to the same conclusion using the chain rule. We don't know the chain rule yet. The motivation for the chain rule is not to be able to do this problem a different way, it's to be able to do problems like this one, which is currently beyond our capabilities. So without further ado, what's the chain rule? Well, the chain rule is kind of complicated. The algebraic statement of the chain rule is what you see in front of you right here. It says that if you're taking the derivative of the composition of two functions, f of g of x, that's equal to f prime of g of x times g prime of x. Note that we have function composition over here and there's function composition over here. It's kind of a strange looking formula. There's a lot going on, but it'll allow us to take derivatives like the derivative of sine of x cubed, if we can look at sine of x cubed and recognize that it's the composition of two functions where the outer function is f of x equals sine of x and the inner function is g of x equals x cubed. That's challenging for a lot of students to look at this and see function composition, be able to tell that the outer function is the sine of x and the inner function is x cubed. If you are able to do that, then all we're missing to use this formula is f prime of x and g prime of x. And the good news is we could figure both those things out pretty easily. If f of x is sine of x, f prime of x is cosine of x. And if g of x is x cubed, g prime of x is 3x squared. With these four pieces of information, I can figure out this derivative by using this rule. This rule tells me that the answer is the product of two things. One of those two things is easy, it's just g prime of x. So my answer is going to be something times something. And the second of those somethings is really easy. It's just the 3x squared that I have written right here for g prime of x. The first of the two things is a little bit more complicated. The first of the two things is f prime of g of x. F prime of x is cosine of x. But you don't want f prime of x. You want f prime of g of x. Note you don't want f prime of g prime of x. You want f prime, the derivative of f, evaluated at g, not the derivative, but just g itself. F prime of g of x is f prime of x cubed. Because remember, when you have composite functions, you work from the inside out, and g of x, is written right here, is x cubed. F prime of x cubed is something that we can figure out, because we know f prime of x, so we can figure out f prime of x cubed by copying this exact line that we see right here, changing all of the x's into x cubed. So f prime of g of x is equal to the cosine of x cubed. What this all tells us is that the derivative of sine of x cubed is equal to the cosine of x cubed times 3x squared. Here's our answer. I hope that you hated this example right here. I hope that you found this really challenging, because there's an easier way, in my opinion, to use the chain rule than just go to the formula of the chain rule, find all the different pieces, and put them all together. Rather than just memorize this as a formula, understanding what this means will make your life a lot easier. So what is going on here is you're supposed to look at the thing that you're taking the derivative of as layers. When you compose functions together, I want you to be able to think about which one is the outer layer and which one is the inner layer. In this specific case, the outer layer was the sine of x and the inner layer was the x cubed. The outer and inner layers are defined as the f and the g that make up f of g of x. Anyways, if you're trying to take the derivative of a composite function, what you do is you take the derivative of the outer layer, leaving the inner layer completely alone. Then you multiply that by the derivative of the inner layer. This is a phrase that'll make the chain rule a lot easier for you. Let me show you how that works with this exact same example. If I were again trying to take the derivative of the sine of x cubed, and I was good enough with function composition that I could look at this problem and kind of see these colors in my mind, see the outer layer and the inner layer in red and blue respectively. Then what I could do to apply the chain rule is I could just focus on the red, completely ignore the blue. I could ask myself the question, what's the derivative of the sine part of sine of x cubed? Well, the derivative of sine of x is cosine of x, so the derivative of sine of x cubed would be the cosine of x cubed. I take the derivative of the red part, completely leaving the blue part alone. Take the derivative of the outer layer, leaving the inner layer alone. That's important. But then I'm not done at this step because I've only taken the derivative of the red, not the blue, so I have to multiply this by the derivative of the inner layer, the x cubed. I got a product of two things. One of those two things doesn't have the d over dx symbol with it, so it's done. There's nothing further that needs to be done to this cosine of x cubed. But this derivative of x cubed still has work to be done. Namely, I have to figure out the derivative of x cubed. Fortunately, that's something I know. It's 3x squared. We end up with the exact same answer that we got over here, but we thought about the problem a little bit differently. We didn't have to write all these steps and do function composition again. We instead thought about the original function in layers, an outer layer and an inner layer. And that takes a while to get comfortable with. And if you ever struggle to recognize which layer is which, we can always go back to our definitions of function composition. But I think what you'll find by the end of this section is that when you're taking derivatives like this, you really don't even have to think about it in terms of function composition. You instead think about it as this new, somewhat nebulous idea of a function being made up by different layers. Two quick comments. One, this should not feel comfortable at all yet. In fact, this shouldn't feel comfortable after this video. There's going to be lots and lots of examples in this section because really the only way, in my opinion, to get comfortable with the chain rule is just repetition, doing stuff over and over again. The second comment is, I'm just telling you that this works. I claim that the chain rule is a thing and that this is what the chain rule is equal to, but I'm not proving it to you at all. I feel a little bit guilty not proving things to you, but this specific proof, it's not really instructive. You don't really get much out of it. So I'm going to skip it, but I'm also going to link a video, another one of these 3 blue, 1 brown, 3 brown, 1 blue, I don't remember. One of those YouTube videos that I've been linking that does about as good of a job as one can to sort of geometrically argue for why the chain rule makes sense. But that's all kind of beyond the scope of our class. What I really want you to get out of our class is the ability to take the derivative of composite functions. And to do that, you need the chain rule. So let's do 2 more quick examples, then I'll end this video. First one, I want to go back up here to sine cubed x. Remember, sine cubed x is the same as sine of x cubed. You might be wondering why I wrote it all red and blue like this. It's because I knew I'd want to come back to this and take this derivative. If we were asked for the derivative of sine cubed x, sure, you could do it with the super product rule, but you don't need to. There's a more direct way to get to this exact same answer. Instead of thinking about sine cubed x as sine of x times sine of x times sine of x, think about it as an outer layer, stuff being cubed, and an inner layer, the sine of x. When you're in an instance like this where you're taking the derivative of an outer layer and an inner layer, what you first do is just take the derivative of the outer layer. Just focus on the red stuff. We're using the power rule here. We take this 3 and bring it down in front, and then we subtract 1 from the exponent to make it a 2. You're used to there being an x right here, but there's not going to be an x right here because we're not evaluating the derivative at x, we're evaluating the derivative at g of x. That's just a fancy way of saying we take this inner function and we leave it completely alone. And then we're done? No, we've taken the derivative of the red part but not the blue part, so we have to multiply this answer by the derivative of the blue part, the derivative of sine of x. The nice thing about the derivative of the sine of x is it's one of those derivatives that you already know. It's equal to cosine of x. So using the chain rule, we figure out that the derivative of sine of x cubed, aka sine cubed x, is 3 times sine of x squared times cosine of x. In other words, 3 sine squared x cosine x. In other words, 3 times the cosine of x times the sine of x squared. That's the chain rule. 2 more quick examples of about this difficulty level. We'll save the more challenging examples for the next video. If you're feeling ambitious, go ahead and pause the video. See if you can color coordinate this question. See if you can recognize what the inner and outer functions are. If you can't, well, I kind of give you some hints right here. The way you want to view this function is an outer layer, the stuff to the 8th power, and an inner layer, x squared minus 9. With my choices for color coordination, the x squared minus 9 would be blue and everything else would be in red. When you think about this derivative, what you want to do in your first step is completely ignore everything in blue. Just take the derivative of the red part. Stuff raised up to the 8th power. Using the power rule, I bring that 8 down in front and I subtract 1 from the exponent to get a 7 over here. I'm used to there being an x right here as the base, but again, there's not going to be an x as the base. There's going to be an x squared minus 9 as the base because I want to leave that inner function alone in my first step. In my second step, I multiply that by the derivative of that inner function, the derivative of x squared minus 9, and if I could just figure out that derivative, I'd be done with this question. Well, good news. This is a derivative that you know. It's the derivative of a sum, x squared plus negative 9. So we take the derivative of each of the terms individually. The derivative of x squared is 2x. The derivative of negative 9, because it's a constant, is just 0. So the derivative of x squared minus 9 is just 2x. So I can replace this expression with just a 2x. I'm done with the d over dx's. I'm done with the calculus. I have something that's equivalent to my final answer. Perfectly fine if you want to stop right here, but as you've seen in these videos, I typically simplify my answers. What I would do is take this 8 and this 2 and call it 16, and then I would write the x before I wrote the x squared minus 9 raised up to the 7th power. What you see in green is equivalent to what we have right here. Either is an acceptable answer. This one's just a little bit prettier. One more example. Again, I really encourage you to try this on your own. This one's a little bit harder, but still I think the right difficulty level for an intro video. What you'll see is these problems do get harder than what we've seen here. First step is we want to kind of think about our color coordination. If you look at this and you see the square root part as the outer function, that's fantastic. I'm going to rewrite it instead of as a square root with the 1/2 right here, because I don't like radical notation. I prefer exponent notation when I'm trying to take derivatives. All this other stuff, the e to the x plus x, is what I'll have left inside in blue. I got an outer layer, the stuff to the 1/2 power, and an inner layer, e to the x plus x. If you're not sure about your color coordination, what you can do is you can write, I think that f of x is x to the 1/2 power, and I think that g of x is e to the x plus x. If I'm right, then f of g of x better be equal to the original question, the square root of e to the x plus x. Try it out. Compose these together and make sure that you recreate this. But you want to eventually get to the point where you don't need to check your answers like we're doing over here. You're confident enough immediately changing this into this. Assuming you can get this far, what we want to do next is take the derivative of the outer red layer. The way we're going to do that is again using the power rule. We'll take this 1/2 and bring it down in front, and then we'll subtract 1 from the exponent. 1/2 minus 1 is negative 1/2. And then we'll take this inner function and leave it completely alone, e to the x plus x. But then we're not done. We have to multiply that by the derivative of e to the x plus x. Now ask yourself the question, is this a derivative that you can figure out? I bet the answer is yes. The derivative of e to the x plus x, because it's a sum, is just the derivative of e to the x plus the derivative of x. And those are two derivatives that we know. The derivative of e to the x is just e to the x. The derivative of x is just 1. So the derivative of e to the x plus x is e to the x plus 1. Note the importance of these parentheses. If you don't have these parentheses here, all this stuff will only get multiplied by the e to the x, not the plus 1. But I want to multiply all this stuff by this entire derivative, so it's really important that I put these parentheses in right here. You could be done right here if you wanted. If you're curious how one could simplify this, one way you could do it is you could put the e to the x plus 1 on the top of a fraction, and then you could put the 2 from this 1/2 down on the bottom of the fraction. And then instead of thinking about e to the x plus x to the negative 1/2 power, you could think about it as e to the x plus x to the positive 1/2 power down in the denominator. And instead of writing it to the positive 1/2 power, I'm going to write the square root of e to the x plus x. This is probably how I'd leave my final answer. But if your challenge is going from this line to this line, that's an algebraic challenge, not a calculus challenge. The calculus was done in this line. That's the chain rule. If you're only feeling a little bit uncomfortable with it at this point, frankly, you're doing better than you probably should be doing. The chain rule is challenging. It's going to take a while to get comfortable with when you see some of the examples that we have coming up. It might be kind of intimidating, but what you'll see is if we pick these apart and go through them really slowly and understand the process, really showing the work in the different lines, they won't be too bad. You'll be an expert with the chain rule by the time we get done with this section.